Good afternoon or good morning, and welcome to this session of the Math Machine Learning Seminar at the IMIS and UCLA. Today is my great pleasure to welcome Xiaowei Lin as our speaker. Xiaowei studied mathematics at Stanford University and did a PhD at UC Berkeley with Ben Struffels. And he spent a couple of years in Singapore at the University of Technology and Design as an assistant professor, and now is back at the Bay Area working as startup company. And but today he's going to be telling us about some of the work that he has been doing the past couple of years on singular learning theory and related things to the relative information. I very much look forward to his talk. And so, Xiaowei, please.
Thank you, Guido. It's my honor to give a talk today. I'm very excited to see this community again. And so today's talk, there's going to be two parts. It's kind of my attempt to mash the two parts together, so you might feel a little bit disjointed in the middle. But my first aim is to talk a little bit about singular learning theory and how it's related, maybe give some hints about how we can look at deep learning or other learning algorithms from that point of view. And the second part, I'm going to talk about time series, how to train time series with hidden variables. Okay, so I would like to keep the talk kind of informal. Feel free to stop me if you have questions, just like shout into the talk and say, I have a question or something like that. I'm not going to be offended. But of course, with most of these talks, most of the time, the questions come at the end. But please feel free to stop me and say, I want to ask you something about this. Yeah. So the kind of question that I have in the back of my head, that one of my favorite questions all these years is, how do we train recurrent networks? So networks that have feedback loops, networks which are statistical, networks that maybe have hidden variables or memory, or maybe spiking neural networks. These are the questions that I like to think about. And how does it relate to the geometry of the problem, the algebra, the algebra and the geometry of the problem? What happens to these networks when time goes to infinity? What happens to singularities in the network? So these are the kinds of questions that I like to think about. So, but before we talk about time series and recurrent networks, I want to first go back to something more safe, static systems, non-time series, right? And then from there, we want to draw some insights about how we should think about these recurrent networks. So let's start with something that everyone's familiar with, maximum likelihood. I hope people know what that is. It's a machine learning seminar. So we have a true distribution, which I call Q, and we have some data, x1 to xn, and I have a model, which is the distribution of x, p of x given w, where w is my parameter for my model. And I have a prior on the parameter set, which I call phi. And the question that many people solve in machine learning is, how do we maximize the generalized log likelihood? And the reason why I call this a generalized log likelihood is because I have this, in addition to the log likelihood over here, which is the sum of the logs of the probabilities, I also have this regularizer term where the prior enters in terms of the log of phi. And of course, you can think of log of phi as maybe like the absolute value of w or your favorite regularizer. And here we need to have some kind of coefficient to tell us how we balance that regularizer with the likelihood. And that coefficient has to vary with the number of samples n. So we are not allowed to have a fixed, most of the time we do not like to have a fixed number an here, like a constant here, because when the number of samples go to infinity, you do want the regularizer to become less and less important, or have a less weight on this likelihood. So a better way to frame the likelihood problem is to think of it as a log likelihood ratio. So we should take the ratio between the true distribution Q and the model P. And so you can see that we are just really adding a constant term, log of Q to the likelihood that we have over here, maybe with a change in sign. And so it really doesn't change anything. But later we are going to see that this log likelihood ratio has properties which are easier to analyze. And so the maximum likelihood estimate will be the parameter that minimizes this generalized log likelihood. And the reason why we're minimizing and not maximizing, because now the model P appears in the denominator of this log and not in the numerator. And so I'm going to call the estimate W hat. And from W hat, I'm going to get a density for predicting the next data point. And that's going to be P of X given W hat from the model. And this estimated density, I'm going to call P star. So in many machine learning models, the goal is to estimate the density of the data. So you have an algorithm that takes the data as input and outputs this that estimated density. And there are many important questions that we want to ask about this estimated density. So one of these questions is going to be about how this density generalizes. So, but before we talk about generalization, I want to introduce a concept that maybe you already know. It's called relative information, but most people like to call it KL divergence or relative entropy. I'm borrowing this word relative information from John Baez. He has this paper where he talks about axiomatizing the properties of the KL divergence. So here I'm going to be calling it relative information or just information in this talk. So we have this function k of the parameter w, which is going to be the integral of q log q over p, where here p is given in terms of w, and this is the information from the model p to the true distribution q. So it's a kind of distance. It's not a symmetric distance, but it's a kind of distance in the space of distributions. And here x is my random variable. So I'm thinking of distributions on a random variable x, and I want to look at the distance between them. So if we go back to the, so if you remember, we had this log likelihood ratio, the log of q over p, and if I applied that to my training data, so I had n data points, x1 to xn, I'm going to get this log likelihood ratio. And it turns out that if you take the expectation of this log likelihood ratio, you can see that this sum will become an integral over the true distribution q, and so we get the KL divergence, or we get the relative information. So if we come back to our maximum likelihood problem, the log likelihood ratio there is going to be the sum of this usual or classical log likelihood ratio with a regularizer term. And now I'm going to show you that to understand the maximum likelihood problem, we need to understand Kn, or we need to understand K. We need to understand the Kullback divergence. If we understand the relative information of Kullback divergence, we will be able to analyze the asymptotic properties of maximum likelihood. What happens when the number of samples go to infinity? So how do we analyze the asymptotic properties? So there's this term that we call generalization error. Let me explain where this comes from. So previously we had the likelihood ratio over here. So it makes sense to talk about the likelihood ratio when we're applying it to test data, right? So if I have maybe n, maybe I should have used a different symbol here. Instead of n, I should use m. If I have m different test data points, I could look at the log likelihood ratio of those test data points and use it as a measure of how well my estimated density is doing. So P star here is my estimated density. Now, if I take the expected value of this test error, I am going to get the Kullback divergence. I'm going to get the relative information from the estimated density to the true density on X, which is integral of Q log Q over P star. And that is going to be the definition of generalization error. So if you ever go to a machine learning talk and they talk about the estimated density, you can always ask them, what is your generalization error? So you're basically asking, what's the Kullback-Leibler divergence, or what's the relative information from the estimated density to the truth? And so for maximum likelihood, the generalization error is going to be the information from P at W hat to Q, and that is just K of W hat, where K was defined previously for a parameter W. Okay, any questions so far? Okay, so now, as I promised, okay, to understand maximum likelihood really, really well, we need to think about algebraic geometry. We need to think about the geometry of the statistical model. And here, I want you to think about the model as a map from my parameter space omega, this blue parameter space here, to my space of distributions, which is this red space over here, probability space, the space of distributions of X. And so a parameter W will get mapped by P to a distribution P given W. And the image of this parameter space is going to be some compact connected space in this probability space. And that's going to be the image of the model. That's going to be the model itself. The model is the image of this map. And now I'm going to make a very big assumption. I'm going to assume that my true distribution is in the model. Okay, so of course, a lot of what I'm going to discuss applies also when Q is not in the model, but I just want to make things simple today. So I assume that my true distribution is in the model. It is a point in the image of this map. And what's interesting is to look at the fiber, the pre-image of the map, of the pre-image of Q under this map. And so I'm going to get this variety in the parameter space, and I'm going to call this the true fiber. So the equation of this variety, this is an analytic variety, is going to be K of W equals to 0. It's a set of all W such that K of W is 0. And here you remember that K has logarithms in it. Actually, we can actually reduce this variety to an algebraic variety, and I talk about this in my PhD thesis quite a bit, but I'm not going to go into that today. Okay, so for now, you're just going to think of K, this true fiber, as an analytic variety in the parameter space. And this variety is going to have singularities. They're going to be crossings, they're going to be cusps. And it turns out that the asymptotic properties or the generalization error of the learning algorithm is going to depend on the structure of these singularities. So to really understand the singularities, we're going to need a tool from the 1960s called resolution of singularities. Okay, so what this means is that we are going to have to find a map from, so now here you can imagine that this pink space here is my parameter space, okay? And I have my true fiber here. It could look really complicated. And I want to find a map from another space to my parameter space such that the singularities simplify. Okay, so the map is almost one-to-one everywhere except for at the singular locus.
May I ask you
and so, yes.
So do you assume that the parameterization is algebraic to begin with?
For this talk, we just assume there's analytic. But in many interesting models, it's enough to assume there's
analytic,
algebraic.
You mean real analytic?
Yes, real analytic, yes. For statistical models, we assume they are real analytic. Yeah, good question, thanks.
But
so
how do you deduce that the pre-image of the true distribution is algebraic?
Yes, that's a very good question. So this is a bit involved. Like we literally have to compare the, so it turns out that K, I lied a little bit. This K function over here is often not analytic. Okay, but I have some work with Matthias Deton and yeah, and I'm sorry, is my memory is not doing me well today, but we can actually show that there's another variety that is algebraic, in fact, that has the very similar singularity structure as okay, I'm not going to say as this analytic variety here because it's not analytic, but the algebraic structure of that algebraic variety is going to give us the generalization error of the statistical model. Okay, and there's some.
No, but you should assume something, right? It's P is just an arbitrary analytic map.
Yes,
so the singularity could be very non-algebraic looking.
Right, it could be really bad. Exactly. So we often have some regularity assumptions. In many statistical papers, they put some regularity assumptions on P. For instance, like P is has derivatives. It's smooth up to some level, and
no, even if it's analytic, so it has all the derivatives, whatever.
Right.
The singularity need not to be algebraic.
Yes, I agree with you. Yeah. So so I think for this talk, I won't go into the details about the some of these more complicated issues. But we if we look at certain statistical models, like let's say hidden, like Gaussian mixtures, or maybe like some kind of independence, not independence model, but mixtures of independence models, we can show that the singularities here are going to be algebraic.
Okay.
Yeah. So I'm sorry about that. Yeah, there are usually some technical assumptions here, which I think will not be very illuminating at this point. But we can introduce enough assumptions that can make the true fiber here well behaved, and they are very reasonable assumptions on the statistical model on P. So maybe I can point to a reference like this book of Sumio Watanabe. He has a book called Algebraic Geometry and Statistical Learning. And in that book, he introduces these assumptions. He has a list of these assumptions that would make the problem well behaved. Yeah. Okay, so we come back to the singularities of so we assume that we have algebraic or analytic singularities in our true fiber, and by a famous theorem of Hironaka, there exists a map from a manifold to this space where the singularities, the pre-image of the singularities have simple normal crossings. So what simple normal crossings mean is that in the pre-image of this desingularization map, the singularities, they look like intersections of coordinate hyperplanes, right? So like for instance, in this picture, we have intersections of these lines here that look like intersections of the lines in 2 space. So and it turns out that you can do this desingularization using a sequence of blowups. So a blowup is an algebraic map, okay, that maps from a space that looks like a Mobius strip to our space, and it basically separates all the lines at the origin here by their tangents. So you can see here that the lines here are separated into different. The lines that intersect here are separated into separated lines in this Mobius strip, and in this resolution singularities, we often describe it with a collection of charts. A chart is a subspace or subset of Euclidean space that has an algebraic map into this space, and the union of these charts is going to describe our resolution singularities. So these charts are going to cover the manifold over here, and then we have our map. So let's assume that we have this resolution singularities for our relative information, for our information. And let's see what happens to maximum likelihood under this map. So we have this resolution singularities from manifold M into our parameter space W. And after applying this desingularization to the relative information K, I'm going to get a monomial locally in each of the charts that look like mu to the power of 2k. And what I mean here is that in the local coordinates mu1 to mu d, I have mu1 to 2k1, mu2 to 2k2, and so on to 2kd. And the reason why we have this power of 2 over here is because this Kullback divergence or relative information is always positive. Sorry, it's always non-negative. It's always non-negative. So this is why we have a square term here. And if we apply that map to the log likelihood ratio Kn, you can prove, it's not easy, you can prove that the result is that we are going to get a function on mu, in each chart, we're going to get a function on mu, okay, that looks like this. So we're going to get mu to the 2k plus a 1 over root n mu to the k times this random variable c plus another random variable which I call OP. And so we know that this Kn is a random variable. So the result on the right-hand side is also going to be a random variable. But what's interesting is that this part here is not random. This is deterministic. This coefficient here is deterministic. We have this random variable here, which is well behaved. It's going to be a Gaussian process on the manifold. And we have this remainder term, which is often messy, but we can show that this remainder term goes to 0 in probability as number of samples go to infinity. So in the limit as number of samples go to infinity, we get this very simple looking function, and which has a random variable that is well behaved. It's a Gaussian process. And we like things which are Gaussian, usually in statistics. And so now we can use that to derive the asymptotic generalization error of maximum likelihood. Okay, so after we apply the resolution of singularities, I'm going to apply a new coordination of my chart using variables, using the coordinates t v1 to vd minus 1, such that t becomes mu to the 2k. Okay, and there's always a way to do this. I'm not going to be explicit, but we will make it such that t absorbs 2 to the 2k, and that the other v's are somewhat orthogonal to the t. And so the result is that we get this generalized log likelihood that we had for maximum likelihood. It becomes t squared plus 1 over root n of t times c plus my regularizer term plus something that's very small. And so this is a nice quadratic equation that is so if you're trying to maximize the quadratic equation, you can ask a high school student to do this. So they now under these new coordinates, it becomes easy to minimize this number here. And you can show as a result of this new form of the log likelihood ratio that the expected value of the generalization error is going to be of this form. It's 1 over 4n of the expected value of the maximum over all the coordinate charts of the maximum in each chart of 0 of c of mu squared. Okay, and this is the generalization error of maximum likelihood. So we have a closed form now for the generalization error, and we can use this to compare maximum likelihood to any other learning algorithms, and we can ask if maximum likelihood is doing something correctly or wrong. And you can also think about deep learning from this point of view, because the objective function in deep learning can be thought of as a kind of likelihood function. And so this is the kind of perspective that we want to be using right now. And the other thing that I want to add is that this generalization error here applies to singular models. So models which are not necessarily regular from a statistical point of view. So what I mean by regular is that it has official information that is full rank and so on and so forth, right? So it applies to singular models such as mixture models and hierarchical models with hidden variables and so on and so forth.
May I ask a question?
Yes, please.
The previous slide, though.
Yeah. This slide, right?
So the mu coordinates are on a blown up manifold.
Yes, that's right.
Yeah, but in which chart?
On each chart, on different charts, they're going to have this form on each of the charts. So on different charts, you're going to have different coordinates. But locally on each chart looks like this.
The random variable c takes value also in the manifold.
That's right. It's a Gaussian process on the manifold, on the chart.
On the chart.
On the chart.
So, but how does this? How is this form is invariant? Is it invariant under the coordinate change?
Yeah. It's invariant. Yeah, you can apply coordinate changes. Of course, the form will look somewhat different. But I think the structure of the singularities are in. I'm sorry. What do you mean by invariant in that sense here? So maybe another way I can say this is that that this is not the only standard form. Depending on your desingularization, you could get other similar forms, but they all look like this. They all look kind of like this. And
all right.
Yeah. So
can I ask another question?
Yes.
And so here, what is the intuitive reason why the t-square shows up? Is this because the relative entropy ends up being convex, or
Yes, that's right. So you can think of this as the fact that the relative information, relative entropy is somewhat like a quadratic function locally. In a regular case, is quadratic. It's described by the Fisher information matrix. But in the singular case, after a change of variables, it remains quadratic in that sense. In fact, if you look at under this this new coordinate system, your relative information k, not kn, all right, just k, it just becomes t squared. So locally, it just looks like a quadratic function. It's just so it has a very simple structure. But of course, we know t, there's a lot going on in t. There's a mu, it's actually mu to the 2k. There's a
so in these new coordinates, what is the equation of desingularization of the true fiber?
The true fiber in the new coordinates.
Coordinates, yes.
Yeah. So to be honest, I don't like this t coordinate system. I'm going to go back to the mu coordinate system.
Yeah, mu coordinates. Okay.
Under the mu coordinate system, the true fiber is going to have this is going to be the zero set of this monomial. It's going to look like it's going to have multiplicities on the different. It's going to be a simple normal crossing. It's going to be the zero set of this monomial, and there are going to be multiplicities on each of the coordinate hyperplanes.
I see. I see. So, but the any point on the true fiber should be a minimizer of R, right?
That not of R, not of Rn. Rn is stochastic. Rn is stochastic.
No, from R, from the mean of Rn.
So Rn is stochastic. So depending on your data, the minimizer is going to change. It's going to be jumping around. Mm-hmm. But if you take the expectation of R, even if you take the expectation of R, you're going to have this extra term with the regularizer. So let me just come back here. If you look at Rn over here, R has a likelihood term and it has a regularizer. If I take the expectation of that to get R, it's going to be k plus this term is not stochastic, so it's just going to be k plus this. The true fiber that I described is going to minimize just the first term, k.
I see.
It's going to minimize the regularizer.
And what's the point of this perturbation?
The regularizer. So this is supposed to help offset some of the bad properties of maximum likelihood. So it's in machine learning, for instance, if you don't have a regularizer, you're going to end up with a model that overfits the data. It's going to over parameterize, and you can prove that if you add some small regularization, like some L1 or L2 regularization, you're going to end up with a sparse model where some of the parameters are zero. And in that sparse model, you can prove also this is for instance, there's a theorem by Terence Tao and Emmanuel Candace, or you can look at Donahoe, where they look at sparse coding models back then. Adding a regularizer will help you to choose the sparse model, the correct sparse model with high probability.
Okay, thank you.
Yeah, so it's a very interesting theory, and people are still trying to understand why this happens. Like, how do you choose this regularizer? Well, it is supposed to offset some of the bad behavior of just using the log likelihood. What we do know is that when you let number of samples go to infinity, all these bad behavior goes away. But in real life, n is never infinity, so you have to add a regularizer to help you. And there is some relationship to singular learning, but I don't have time to go into this today. My thesis, I talk a little bit about this. Watanabe's book also talks a little bit about the effect of the regularizer.
Okay, thank you.
Example here. So if you look at my theorem here for asymptotic generalization error, it's only for the case when there's no regularizer, right? The case when the AN is non-zero, when there's a regularizer, is discussed in Watanabe's book. So he goes through all the cases. I don't do that in my talk here. And he has a different form for all those other cases for the generalization error. So it's an interesting topic.
May I ask a question?
Yes.
So you're writing here, apply resolution of singularities. So it means in practice, you are using some software to compute it, right? What would you use as such?
So yeah, that's a good question. So there's so if you want to resolve singularities, you could use a software called Singular, or Macaulay 2 also has some capabilities there. Okay, but I would say in statistics, people have not been using those software to analyze their models. Even just to talk about varieties and stuff like that in the statistical community is difficult. But so in practice, in real life, few people actually apply resolution of singularities to their models during learning. But if you have a favorite model, like let's say a mixture model, and you want to understand what's going on asymptotically, so this would be the approach. The approach would be to find the resolution of singularities in general for all your different models, and then to analyze what happens to the generalization error. So this would be the strategy.
Okay, thank you. Do you already have a success story in this direction that's such that resolution of singularities are bringing some light to the people?
I hope the second half of the talk would be somewhat in that direction. I'll explain a little bit more. So that's a good question. So maybe you can hold that question for a while. I hope I can answer that at the end of the talk.
Looking for it. Thanks a lot.
Yeah, that's a really good question. I really want to get there. Okay, so we've talked a lot about maximum likelihood. Now I'm going to talk about Bayesian inference. Oh, by the way, if I don't get to the end of the talk, I'm actually fine. But I think it's more interesting that people learn something nice. And maybe, I'll talk about the other stuff another day. But here, let's talk about Bayesian inference, right? So Bayesian inference is a different way to do learning. And here in Bayesian inference, you have some data, dn, and then you have a prior, which is P of W, and then you use Bayes' law to update your prior to the posterior on your parameter space. So this is given, the posterior is called P of W given dn. And this is Bayes' law over here. So I want to show you that in Bayesian inference, we can also rewrite this in terms of relative information. So what I would do is I'm going to normalize the distributions here by dividing by the true distribution. Again, I have this likelihood ratio. And then this, if you expand it out, it will become like this. It's going to be the initial prior phi of W times e to the power of minus n kn, which is my log likelihood ratio, right? Divided by z, and z is a normalization factor that makes this thing a probability distribution. So zn of 0 is going to be the integral of this entire thing over W. Okay, so it's going to make this into a probability distribution. So once I have my posterior, how do I get an estimated density on a new data point? That's going to be given by P of x given W, my model, times the posterior. So instead of multiplying by the prior, I now multiply by the posterior. And you can show that, okay, it's going to be the ratio of P of my new data point x and the data set dn times the O prior divided by the integral of the data, the likelihood of the data times the O prior. And this ratio is going to be my estimated density. So the generalization error of Bayesian inference is going to be the relative information from Q to P star. And after simplification, you can show that it's equal to the log of my marginal likelihood integral minus the expected value of my log of the marginal likelihood integral with one extra data point, n plus 1. So if we want to understand the generalization error of Bayesian inference, I will need to understand the behavior of the log marginal likelihood integral. I need to understand the behavior of the log marginal likelihood integral. So here, again, algebraic geometry comes to save the day, right? So instead of looking at my marginal likelihood integral, I'm going to look at the same integral, but with kn replaced with k. And so this is going to be, this form here is going to be a form known in physics as the Laplace integral. And you can apply something called the Mellin transform to the Laplace integral to get a zeta function. Okay, so there's a lot of connections here to physics and number theory, the zeta functions. This is related to Riemann zeta function and other zeta functions that people look at in number theory. And it turns out that if you have a desingularization of k, so k composed with rho here becomes mu to the 2k, then we know how to find the poles of the zeta function. All right, so here's a simple example. If you have k rho equals to mu to the 2k, and that if the Jacobian of rho is also some monomial mu to the h, then your zeta function becomes the integral over the chart, this small chart here, 0, 1, this cube here, hypercube here, of mu to the minus 2k z plus h. All right, so z here is my variable for my zeta function, and it has a nice closed form, right? So you can ask a high school student to do this this integral. It's a simple integral in calculus, and the poles are going to be the values of z that make the terms in the denominator go to 0. So the poles are going to be of the form hi plus 1 over 2ki, and possibly with multiplicity if 2 or more of these terms in the denominator go to 0. So these are the poles. They're going to be rational numbers, positive rational numbers. The poles of the zeta function are positive rational numbers. So now if I so in general, if you have a function k, okay, then the real log canonical threshold, I'm going to define this term, the real log canonical threshold of k is going to be the smallest pole of its zeta function. And the multiplicity of that pole is going to be m. And so the real log canonical threshold is going to be this pair, lambda m, where lambda is the smallest pole and m is the multiplicity. So so you can actually prove that once you have a desingularization of k, you then, as a result, know the asymptotic properties of your marginal likelihood integral. And it turns out to be minus lambda of log n, where lambda is your real log canonical threshold, and time plus n minus 1, your multiplicity of log of n, plus some extra terms. This is a random variable here. This is something that goes to 0. So here I have, you see, I have this deterministic behavior here with a constant random variable plus something that goes to 0. And if you go back to the Bayesian generalization error, you can show that it is therefore equal to lambda over n plus something small. And so, in other words, for Bayesian inference, for using Bayes' law to update your posteriors, your beliefs, the generalization error is related to is basically the real log canonical threshold divided by n. This is an amazing result. I mean, it shows you that there's a deep connection between learning and algebraic geometry, the structure of singularities, because these real log canonical thresholds are being studied in a complex algebraic geometry all the time. Okay, and also this tells us that this generalization error is small. It's small compared to the generalization error of maximum likelihood, which has this max of Gaussian process in there, which often the behavior is very hard to analyze. Okay, so there is a conjecture that for many models, this generalization error of maximum likelihood is a lot worse than the generalization error of Bayesian inference. And so this is why maximum likelihood performs poorly compared to Bayes inference.
I have a quick question about that.
Yes.
So when you did the maximum likelihood estimation, you were doing some regularization, right? So I was just going to see, could you compare that regularization with what's going on in the Bayesian case? Because I almost interpreted the regularizer kind of as waiting by the prior. So I was curious. It's a
that's a good question. So it does help a little bit, but not But long story short, it does help a little bit, but not much. You can show that there are some issues here. The big issue here is we don't know what regularization to pick in general. If for specific models like linear models, maybe mixtures of Gaussians, not even mixtures of Gaussians is hard. Like for certain models, you can show that, okay, a certain regularization will work well for that class of models. But in general, if I give you a deep neural network, we don't know how the L1 is going to perform. We don't know if it's going to be enough to offset the bad behavior of the other terms. So this uncertainty makes it hard to work with just the regularizer. But it's supposed to help. It does help a little bit, but if the gold standard, basically the message here is that the gold standard is Bayes inference. If you had a computer that's powerful enough to compute marginal likelihood integrals, that's powerful enough to compute the posteriors and to store all these posteriors over all the points in the parameter space, then that's the best way to go. You cannot do better than that. Conjecturally, you cannot do better than that. We don't know if there's any. So far, we haven't found a learning algorithm that has a better generalization error than Bayesian inference. That's a conjecture, sorry.
Okay, interesting. So the difference is in the first case, you're just waiting by the prior, but in the second, in Bayesian, you're actually using the posterior information.
That's right.
Okay, I was just trying to understand on an intuitive level. Yeah, thank you.
That's a good question. Yeah, instead of picking one point in the parameter space, I'm picking a whole fat distribution over the parameter space. So it's a big cost to pay for better generalization. So to some extent, when I look at this inequality here, I see two extremes. I see Bayesian inference as the gold standard. I see maximum likelihood as a good enough but not really that good alternative. And in between, there's a whole spectrum of other things like regularization and so on. And my goal is to analyze what goes on in between these two limits, in this spectrum. And so this brings me to so this brings me to the last slide here on singular learning, right? So there's been a lot of talk in deep learning about this flatness of minima, right? That we should be looking at local minima that are somewhat flat, that has and these flat minimas, you measure the flatness using curvature. Okay, in deep learning, sometimes they use the Gaussian, they use the Riemannian curvature to measure the flatness, and people believe that when the curvature is more flat, you get better generalization from the learning. That is somewhat not true. Okay, and here's why. Okay, so we have a better way to think about flatness is actually to think about this integral. So you imagine that I have my callback, my relative information. Okay, it creates some kind of a landscape. Now I'm going to fill the landscape with water. Okay, so I'm going to fill it with water. So this is my landscape here in green. I'm going to fill it with water up to a certain water level, which is 1/n. So for all the callback for all the relative information less than 1/n, and this integral is over the water is going to get filled up, and the amount of water is going to be the integral of the prior over that parameter space, because we think of the prior as a measure over the parameter space. So I'm looking really at the measure in that puddle that I created, okay, in that level set, in the volume below that level set. So this volume is very related to this stochastic complexity here, the log of the marginal likelihood integral. It has the same form, which is minus log n minus 1 log n. It is the exact same form. You can prove this. So it turns out that if you want to pick a good model, you want to pick.
I have a quick question.
Yes.
So this integral is on desingularized manifold?
No, this is on the original manifold.
On the original, okay.
Yeah, original manifold W.
Yeah, all right.
Yeah.
Thank you.
And if you desingularize it, then you can actually study its properties as well. It turns out that you can do Laplace transform to this, to get the Laplace integral, and then you apply a Mellin transform to get a zeta function. So all these functions are related. And so if you are trying to find a good model, you will want to find one with the smallest generalization error. It means that you want to find a parameter that has the smallest real log canonical threshold, which means that you want to find the parameter that has the largest K neighborhood, right? K neighborhood meaning this water level thing that I talked about. What's the volume of the tubular neighborhood given by K? And this is the best way to measure the curvature or the flatness of the likelihood function, sorry, of the objective function, okay, and not the Riemann.
I have another question. So
please go ahead.
Yes. How come Vn is not asymptotically zero? Why does it grow actually?
It's growing because as n goes to 0. Oh, let me think.
No, n goes to infinity.
Yeah, sorry, as n goes to infinity. Good question. Let me see. Must have made a mistake.
I think even monotonicity properties of it's a log Vn. I'm sorry, it's a log Vn, of course.
Sorry, Vn goes to 0, log of Vn goes to minus infinity.
Yes. It's all right. I'm sorry.
Sorry. Yeah, thanks for pointing that out.
And I have another question. How come it doesn't depend on phi?
There's a there's a constant c that depends on phi. I'm sorry. Here, it does depend on phi, but it goes in a constant term. Oh, and one more thing. Phi has to be somewhat smooth. Phi has to be positive. Okay, there are several cases, but the simplest case is when phi is positive over the entire parameter space. It has no zeros. But if it has zeros, then the V is going to introduce singularities into this V.
Mm-hmm.
And this will change. That comment is also relevant to everything that I've discussed before. Phi actually will introduce singularities into this if phi has zeros. So we're going to assume that phi is positive everywhere. I hope that helps. Yeah, that's a good point. Thanks. I'm sorry, I oversimplified a lot of stuff here. Maybe that's not good, but I wanted to keep the big picture in most of this. But the details are in the books are more thorough. The textbooks are more thorough on this. Okay, so anyway, I was saying that Riemann curvature is not the right way to measure. The better way is to look at this tubular volume. And there's a nice interesting paper from last year from a bunch of from Daniel Murfett and a few other people in Australia, and they wrote this paper, but in the end it didn't get published, which I was very sad about. They submitted to NIPS, and in that paper they talk about this issue quite a lot. Very nice paper. Okay, so I have 10 minutes or less. I'm going to just give a brief overview of recurrent networks. Okay, so I promised that there was this two extremes, which is maximum likelihood and Bayesian inference, and I promised that I would look at the things in between. And the way to look at the things in between is to use something called variational inference. Okay, so what is variational inference? Let me just first start by defining something called generalizing my relative information to something called conditional relative information. Okay, previously I had the information between P and Q on some random variable X. Now, instead, I'm going to say, what is the information between P and Q of Z given X? You should think of this X as maybe something that we observed, and then we ask, now what is the information on Z given that X has been observed? What's the distance between two distributions now that X has been observed? And so the way to do this is to look at the KL divergence or the relative information of these two, of Q, log Q over P, but for the conditional distribution of Z given X. And then now I have to average it out over the true distribution of X. And you can prove as a result, it's not difficult, that the information on Z and X is equal to the information of Z given X plus the information on X. So if I want to construct the information on everything, I can first find the information on X, then I find the information on Z now that I'm given X. So this is a very intuitive from the measurement point of view as well, that information can be structured in this hierarchical way that you can measure something first and then try to measure something else after that first thing is measured. So because all of these information measures are positive, I can now show you that you can see that this information on Z and X is going to be an upper bound on the information on X. And this is kind of the big idea behind variational inference, that if you want to optimize, let's say, the information on X, then one way to relax that is to look at the upper bound, this upper bound, and try to minimize this upper bound instead of minimize the original information on X. So that's variational inference in a nutshell. But I want to go a bit deeper. Why does variational inference work? Okay, so here, variational inference, right? The goal was to minimize this information on X. Now, instead, we're going to minimize the upper bound on Z and X. And now that I have these two variables, now that I have these two variables, Q and P, I'm going to do an alternating optimization. So first, I fix P and I vary Q. So previously, I couldn't vary Q, right, up here, because Q of X was the true distribution. I cannot vary the true distribution, it's fixed. But now that I've introduced some hidden variable Z, okay, some extra variable Z, and where Z is under my control, I'm allowed to specify what is Q of Z given X. This is some extra parameter that I have now in the distribution here. So I can try to optimize over this extra parameter here. And then in the second step, I fix my Q and optimize over P, the generative distribution P. And one of the simplifications we do here is that we, instead of optimizing this over Q, the true distribution, I often sample from Q. Okay, and I get a simpler optimization problem here, and then I try to solve that. And so this feels very heuristicy, right? Heuristicy, if that's a word, because I have some sampling from a true distribution, and there's no guarantee this alternating optimization with sampling in the middle is ever going to converge, because the sampling will introduce noise, it will introduce to the problem. And the amazing thing is that you can actually prove for a large class of models that this will converge. And the proof techniques require things from an area called stochastic approximation, Robbins-Monroe, and so on. Okay, very, very interesting theory in itself. But you can prove that often this stochastic strategy here will converge. And one example, in a classic example, is called expectation-maximization, where, okay, so in the first step, right, I fix P and optimize over Q. So you can see that if I do that, it becomes the optimization of this conditional distribution, conditional relative information. Okay, so the optimal one is going to be Q when Q is exactly equal to P of Z given X. And in the second step, I'm going to fix Q and optimize over P. And in that step, I'm going to end up with a function called L, which is some kind of expectation, and minimizing this joint relative information is going to be equivalent to maximizing this expectation. And so this is why it's called EM. EM because there's an expectation and there's a maximization. Okay. So I want to show you that maximum likelihood is also a special instance of variational inference. Okay. So it's kind of a trivial example, because here when I'm in the first step, when I fix P and I optimize over Q, there's nothing to do, because Q, the true distribution here, is fixed, it's the true density, so there's nothing to do. But now when I optimize over P, I'll end up finding the maximum point, the maximum likelihood. But there are two ways to find this maximum likelihood point. The first way is that I'm going to sample n points from Q. That gives me a sample of the objective function, and then I compute the gradient and I descend. The second way is that I don't sample yet. I just compute the gradient of K with the true distribution in all its glory in there. And then I sample the gradient, and then I descend. And so this is often in deep learning called stochastic gradient method. Okay, and we know that the stochastic gradient method performs better than the maximum likelihood method, because we know that it performs better empirically. We don't understand why often, but empirically, it often ends up at parameter points which have flat minima and generalizes well on the test data and so on and so forth. Okay, and from singular learning we can see why, because when you do this, you're going to end up exploring the parameters which have big KW neighborhoods. Okay, so we have to think about this a little bit more, but I think there's an interesting research direction if you want to look at this. Bayesian inference is also an example of variational inference. Okay, maybe I'm not going to go through this step, but the point here is that we have this framework which I call variational inference. I could think of maximum likelihood as a special case of that. That's one extreme. I can think of Bayesian inference also as a special case of that. That's the other extreme. And the moral story is that to get everything in between, I also claim that variational inference is going to get us there. Okay, so I think I'm going to spend the next 3 minutes explaining that part. How are we going to get the things in between with variational inference, and then I'll stop there. I don't think I have time to go to the recurrent networks. That's okay. A lot of that is going to be on my website, so you can read up on there, and I'm going to share the slides. But I just really want to talk about why variational inference is really the way to think about this. So let's go back to variational inference. So we had this z variable, okay, and we have this x variable, and we're looking at the relative information on z and x. The way I like to think about x is that x is like a sensor. The random variable x is like a sensor, is things that we observe, and the distribution q of x is unchangeable, it's immutable. We cannot do anything to change it. Z often in variational inference is thought of as a hidden variable, something like the labels of some mixture model and so on. But I like to think of Z differently. I like to think of Z as a kind of memory, like a RAM or something that you have in your computer, in your hard disk. And this Z is able to help us store information. And the nice thing about Z is that Z belongs to me. I own the RAM, I own the hard disk. I'm allowed to change the values on Z. Even if Z is stochastic, I'm allowed to change the distribution of Z. So Z is completely in my control. And the distribution of Z is the distribution of Z given X. And this is, I call it mutable. So Z, I'm going to call it a mutable variable. Instead of calling it a latent variable, I'm going to call it a mutable variable because there's nothing hidden about Z. There's nothing latent about Z. Z is something that I can change. I call it mutable. And so I think of Z as a memory variable, a mutable variable, and X is a sensor variable that's immutable. And now the conditional Z, Q of Z given X and P of X given Z, they are computations. They are stochastic computations because given an input X, I'm going to give you an output Z. Okay, so those are computations. The discriminative conditional Q of Z given X, it will infer structures from the observations, mathematical structures, logical structures, and the generative distribution will predict observations from the structures. And therefore, when we come back to the chain rule for variational inference, we see that we started off with trying to optimize over X, and then we generalized by optimizing the upper bound. There is going to be a gap between the upper bound and the original problem we are trying to solve. And this gap is precisely the information of Z given X. And so what is Z given X? Z given X is trying to measure the distance between P of Z given X and Q of Z given X. In other words, when I started out with my generative model P of X given Z, my model is going to try to invert that, do some base inversion, P of Z given X to invert Z and X. And Q is my attempt to do that inversion. And if I can do this inversion perfectly well, where I can set Q exactly equal to P of Z given X, this information will go to zero. I get a zero gap. But if I'm not able to do inversion well, this gap is not going to be zero. It's non-zero. And this is actually a measure of computability. If we cannot do this inversion, if we cannot compute this inversion, then it puts a limit on what we can learn. It puts a limit on what we can learn. Okay, so for instance, in deep learning, there's something called VAE, or Variational Autoencoder. There, they put some limits on what Q can be. Q must be a neural network. And so if you are trying to invert your Bayes rule using a neural network, it's going to put some restrictions on how far you can go with inversion. And that restriction is going to be this gap that shows up here. And you cannot do better than that. In other words, if you only allow yourself to use neural networks to do inversion, then your learning can only reach a certain level. It cannot do better than that. There's a barrier to learning, theoretical barrier to that learning. I also like, besides this compute perspective, I also like this sheaf perspective. Okay, so I like to think of my distributions over X as some kind of base space, and then the distributions over Z and X as some kind of total space over my base space. And so I have a projection pi from the total space to the base space, and that's a bundle. Okay, and this bundle acts by marginalization. So I marginalize out Z to get my distributions on the base space. And so all these conditionals the computations that I talked about over here, they are sections of my bundle. So they are mapped from the base space to the total space by multiplying by this conditional distribution. So P of X times P of Z given X gives me P of X and Z. And so when I'm optimizing, when I do variational inference, I'm changing my optimization problem from over the base space to an optimization problem over the total space. So I'm somewhat, so this is like a very common strategy in math where you cannot solve a specific special case. What you do is you generalize that and then you project it back and you try to your special case. Okay, so why am I so interested in this sheaf perspective? And the reason is because if we talk about sheaves, we can talk about something called topos or type theory. Okay, and with this sheaf perspective and type theory, we can finally do logic on my family on my statistical models. Okay, so if I don't have time to go into a lot of the details, but the idea is that I have these statistical models on X, on Z and X, on Z and Y and X, on Z and Y and W and X, and there are these different hierarchies of statistical models. And these hierarchies actually tell us the logical structure on these random variables. And this information measure, relative information, helps us to find the right structure, right logical structure that will help everything to make sense. And yeah, and so that's kind of like what we hope to do in real life, right? You observe lots of data about the planets, about the sun, and then you hope to find structure in there. You find Kepler's law, you find Newton's law, you find Einstein's law, and these are different structures of logical theories on top of the observations. And somehow all these different structures have to minimize something called like have to satisfy Occam's razor, right? You have to find the simplest theory possible. And so we need a way to measure how simple these theories are. And here relative information is a measure of the information in all these different theories. Yeah, so I think that's all the time I have today to talk about this, but that's kind of the big idea in variational inference, that we can think about the computations in terms of these computations and minimizing the gaps. And if you go back to my website, I do talk about how you then use this to think about time series. And you can use that then to derive a learning algorithm on the time series. And that provably converges. Yeah. Okay. Yeah. Thank you very much.
Okay. Thank you so much, Xiaowei, for this very, very nice overview of many different topics. So with this, I'm going to stop the recording, and then we're going to have some space for questions and discussion.